Welcome to Get Your FRQ On. This question is from 2008. It is question 3 and it is calculator active. The link to the question from the free response test is linked to in the description. I'm not allowed to publish it on YouTube, but you can click on the link and access it yourself. In this question, we have an oil spill. We have oil leaking into a pool of oil, and the oil is in the shape of a cylinder. In part A of this question, if we're given that the radius of this cylinder is 100 centimeters and its height is half a centimeter, and that dr dt is 2.5 centimeters per minute, calculate dh dt, the rate at which the height of this cylinder is increasing. So using the formula for the volume of a cylinder, V equals pi r squared h, we can find a relationship between these values by using implicit differentiation. Specifically, we're going to find a formula for dV dt, even though dV dt is not actually what we're trying to find. But if I take the formula for the volume of a cylinder and I differentiate, dV dt is going to be pi times, and then notice that this is a product. R squared times h is a product of two implicit functions, so we're going to use the product rule. We're going to get r squared times dh dt plus 2rh dr dt. And then subbing in the values that we do know that the radius is 100 centimeters, we know that the height is half a centimeter, we know dr dt is 2.5 centimeters. We can get a formula for dV dt that is only in terms of dh dt. So if we simplify this, we get 10,000 pi times dh dt plus 250 pi. However, we do know that dV dt from the question stem is just 2,000 cubic centimeters per minute. So even though we used implicit differentiation to find a formula for dV dt, we do actually know the value of dV dt, and now we have to use it to find a value for dH dt. So we're going to have to use the fact that dV dt is 2,000. So plugging 2,000 into the equation above and solving, we get dH dt is about 0.039 centimeters per minute. In part B, we're given that a recovery device has been put into this oil spill to remove oil from the spill, and that works at a rate of 400 times the square root of t cubic centimeters per minute. We also know that the volume of oil in this cylinder is still increasing at 2,000 cubic centimeters per minute because that's how fast it's leaking out. When is the volume of oil in this spill at a maximum? All right, well, oil is leaking into the spill at a rate of 2,000 cubic centimeters per minute, while oil is being removed at a rate of r of t cubic centimeters per minute. Note that this function f of x equals 2,000 minus 400 square root t is differentiable for all positive values of t. And this is important because we're going to need to take a derivative here or make some assumptions about this particular expression, which may require that it be either differentiable or continuous. So dV dt, now that this recovery device is activated, is no longer just 2,000, it's 2,000 minus 400 square root t. And the volume can be maximized either at an endpoint or somewhere in between where the derivative is equal to 0, so when is dV dt equal to 0? Well, dV dt is going to equal 0 when 2,000 is equal to 400 square root t. And solving that equation for t, we get t equals 25 minutes. The second derivative of v with respect to t, if I differentiate again, I get negative 200 over the square root of t. And note that if t is positive, which it should be, this expression will always be negative when we evaluate it, which means that the curve would be concave down. And if it's concave down, that means this point where dV dt is equal to 0 would be a maximum. Right? So therefore, the function representing the volume of oil in the spill is concave down for all positive values of t, which means the maximized oil is at this point where T is equal to 25. In part C, 60,000 cubic centimeters has already leaked into this oil spill, and we are asked to write an integral indicating how much oil is in this spill at time T at the T that we found in part B. Notice that this seems suspiciously like an initial value problem. So if our rover or recovery device is removing oil at 400 square root T cubic centimeters per minute, and it's being leaked into at a rate of 2,000 cubic centimeters per minute, the rate at which the volume of the spill is increasing after that recovery device begins working is this function we found, 2,000 minus 400 square root T. So the actual amount of oil in the leak at some time would just be a definite integral. But 60,000 cubic centimeters has already leaked in, and we want to know how much is in there when the oil is at its maximum. That's the value of T we found in part B, which is 25 minutes. So that would be 60,000 plus the integral from 0 to 25 of this new rate function, 2,000 minus 400 square root T, would be the integral that would give us that. We're not asked to evaluate this integral, so we don't actually have to evaluate it. You could if it's calculator active, but you don't have to. I think they just don't see the point in having you use your calculator to find that value. As long as you can come up with the integral itself, they know that you are familiar enough with the calculus.